It's Jesse Knight from Unity Health Toronto. He works for Sharmiza Mithra, who is a member of the MFPH network, and he'll be going over his talk today. So welcome, Jesse, and feel free to share your screen and begin.
Thank you. And thank you to the Fields Institute and Maverick Public Health for setting up this opportunity. I will begin sharing my screen here. I think people can see that.
Yes, we can see it.
Perfect, thank you. Just gonna move that out of the way a little bit. Okay. Yeah, so this talk is entitled Beyond Instantaneous Partnerships, Re-examining the Force of Infection Equation in Compartmental HIV Transmission Models. So as part of my PhD thesis, which I recently finished here at U of T and at the MAP Center for Urban Health Solutions at Unity Health Toronto, I modeled HIV transmission in the context of Eswatini, which is the highest HIV prevalence in the world country. And my whole thesis really focused on re-examining, as the title suggests, lots of different assumptions that get made within these models. And this talk focuses on one kind of major chapter within that thesis, where I just focus on this force of infection equation, or for people coming from a different epi background, it's basically the incidence equation or the rate at which new infections are modeled to occur within the modeled system or population. So just by way of outline, I'll first talk about the motivation for this work, which I already alluded to, was modeling HIV in the context of sex work and Eswatini. I'll discuss the idea of an instantaneous partnerships, why we model partnerships as instantaneous, how we actually do that mathematically, and some issues that kind of derive from those assumptions. I'll next introduce the effective partnerships adjustment, which is a new approach that we introduced within the thesis to model partnerships in a different way, and which overcomes some of those issues that I'll describe in a second part. And finally, I'll talk about some experiments where we integrated these various approaches into a compartmental model that I had built as part of my thesis, and we'll compare how they influence the model outputs that we simulate. And finally, the shares can be perhaps shared after. Actually, I forgot to check. Maybe they can be posted on the website, but that includes some more math about this. And we have a publication forthcoming that will dive into those gory details as well. So the motivation for this work, as I mentioned, it's modeling HIV in the context of Eswatini and with a special focus on sex work. And our research question at the very start of all this work was really what types of unmet needs are driving HIV transmission in Eswatini. So unmet needs could be lack of access to effective prevention or treatment for HIV, which can prevent onward transmission. And so there's many different ways that we could conceptualize unmet needs in this context. And so as a result, we tried to build a model which captured a lot of the different routes of transmission that could be simulated, just focusing on heterosexual HIV transmission. So we're not going to examine other types of transmission of HIV in this context. The model structure included 8 different risk groups. So we have 4 groups of women and 4 groups of men. So the women and men in the first level of sexual activity, that's what this dimension is going to be corresponding to here, have essentially 0 or 1 sexual partners within the last 12 months. And they are not engaged in sex work in any way. So the men are not buying sex and the women are not selling sex. The second level of sexual risk was those who had 2 or more partners, but who had no engagement in sex work again. Then we have 2 different stratifications for sex work, including men who are buying sex as clients, as we often refer to them, and women who are selling sex, which we'll refer to them as FSW, female sex workers, throughout the presentation. And we substratified each of those risk groups into lower level of activity, so selling sex not as often, or higher levels of sexual activity, even within sex work, and likewise for clients. So these are the 4 kind of compartments, if you're familiar with those terms, with these compartmental type models that we conceptualize for our level of sexual activity. Sorry about that. And then we will further stratify these 8 levels of risk groups into different states related to the infection and some other factors that we'll discuss later. So we also conceptualize 4 different types of sexual partnerships. So the first type have a duration of between 14 and 19 years, which we derived from some simple analysis on some available data. And those essentially reflect main and spousal partnerships. So they're obviously quite long. They have relatively lower levels of condom use and relatively higher frequencies of sex. We also have casual partnerships, which are obviously much shorter. We conceptualize them as 3 to 18 months. Those generally have slightly higher levels of condom use. Then we also have one-off sex work partnerships, where it's really just a single sex act, as well as regular sex work. So the data suggests that the same client may visit the same female sex worker multiple times over the course of some kind of relationship, and that is what that final partnership is intending to reflect. The reason that there are some ranges given for these different partnership types is that we really have uncertainty as to the average duration of these partnerships. And so when we are actually calibrating the model, which is to say, we put some model inputs into the model, and then we project the model forward and see whether the model is able to reproduce other types of data, like prevalence over time or incidence over time. So there's been surveys that have estimated those. And as part of that calibration procedure, we then try to infer what are some more plausible values within this range of the duration of casual partnerships, so that the model is consistent with those other types of data. That's a very brief summary of model calibration. So let's talk a little bit more about how we actually quantify partnerships from those survey data. So these are the numbers of sexual partners that people have as specified within the model. A typical survey might ask a question like, how many sexual partners, which we denote as X, did you have in the past 12 months? And that past 12 months is what we call a recall period. So we'll denote that as omega here. And what I want to highlight is a little bit of a gotcha that we thought carefully about in terms of how we can interpret answers to this question. So if this is this recall period here, and X, again, is the numbers of partners that would be reported for that period, for these very long types of partnerships, maybe that partnership was ongoing throughout the whole duration of that recall period. And so the person might still report they had one partner, but really the duration of that partnership defines how often there would be a new partnership formed, if at all, because some people may end their spousal partnership and then never form another similar partnership again. For these casual partnerships, which are a lot shorter relatively, someone may report 2 partners within this recall period because one was ongoing when that 12 months started, and then they broke up and formed a different one, and so they might report 2 for the answer to that question. For these one-off partnerships, maybe someone happened to have about 4, and there's lots of different sources of bias regarding recall of those types of data for this type of question. But assuming that they actually had 4, then they would report 4 because there's really no ongoing partnerships that are going to get captured when the duration is so short like that. And finally, we could have these regular sex work partnerships or kind of repeated contact with the same client and sex worker. And in those cases, we may see that they have also reported 2, but the relative rate at which these casual partnerships shown in purple here is actually much slower than the rate of these casual or these regular sex work partnerships, despite the fact that they both only reported 2. So there's a bit of measurement error. But the other thing that's critical to note is that we're actually observing more time with this question than just 12 months. And the amount of time that we're observing is it's in some way proportional to the durations of those partnerships because of the fact that these partnerships can be ongoing at the start of that recall period, so 12 months ago, or that partnership could indeed be ongoing now at the moment of the survey, and it may persist for some months or even years later beyond that survey question. Now, if the survey beginning or the survey, the recall period beginning or the recall period end happens to fall at a random time point within an ongoing partnership, then that's effectively a uniform distribution because it's totally random when it might intersect that time. And as a result, the amount of time that the survey question is actually perceiving is effectively extended backwards in time at the start of the survey and forwards in time at the end of the survey by half of a partnership duration. So because the mean of a uniform distribution is technically halfway through whatever its 2 endpoints are. So the key insight that we had here is the fact that we're actually observing a longer period with this question than the recall period that we specify because of this issue of ongoing partnerships. So our effective recall period that we are going to define for quantifying these partnerships, which is the goal here, is basically the reported recall period plus the duration of those partnerships. Then what we can do is actually quantify a partnership change rate, which is going to be how many partnerships they reported during that time, divided by the effective recall period, or omega prime here. So this is the typical way that partnerships are quantified. And as we get into the math of some of the later slides, I will see where this partnership change rate becomes useful. And the other approach that we could do to quantify these partnerships is you could say, at an average moment in time, how many sexual partnerships does the average person have in a particular risk group? So if we wanted to quantify the partnerships that way, we could say the current numbers of partners are going to be that rate times the average duration of those partnerships. So if you form a new partnership roughly every year, let's say that was the rate, and each partnership lasts on average half of a year, then on average you'll have half a partner at any given time, or 0.5. You get the idea. So this is one kind of tiny little part of this of the thesis chapter where we were exploring this type of thinking carefully about these data. So now let's talk about this instantaneous partnerships issue. The rationale for modeling partnerships as instantaneous derives from the following problem. When we simulate these models where we treat people as groups of homogeneous compartments, that's the kind of classic approach with these compartmental models. We say all the susceptible people are in this compartment, and we could substratify that like by sexual activity, as we did, as I explained earlier. But within a given compartment, all of the people are assumed to be completely interchangeable from one another. And so their history leading up until their entry into that compartment is not tracked, and they're indistinguishable from every other person within that compartment at that time. That's what we mean by homogeneous and memoryless. But the implication of that for the purpose of sexual partnership modeling is that we can't track how many sex acts occurred with a given partner before transmission occurred, and each of those sex acts would be considered to be at risk of transmission if one of those partners was infected. But then there's also a whole proportion of sex acts which occur after transmission already occurred within that partnership, and those sex acts are not actually at risk of transmission because both people are already, in the case of HIV, once transmission occurs, both individuals will be infected, and then they're no longer at risk of transmitting to one another. So the solution that has been proposed previously is to estimate a cumulative probability of transmission per partnership. So that probability approaches 1 if the partnership and level of sexual activity within the partnership is enough, like enough sex acts essentially. It approaches 1, but it can never exceed 1. And the difference between the probability of transmission per sex act times the total number of sex acts, that would be some linear relationship that goes off to potentially infinity if the numbers of sex acts go off to infinity. But the difference when we calculate this cumulative approach is that it can never exceed 1. And so it's kind of bounded. And that, in effect, indirectly accounts for these sex acts which occur after transmission, which are no longer at risk. So once we have this probability of transmission per partnership, then we multiply that by the average rate that partnerships are changing. And so if there's 100 people in this S compartment and 100 people in this infected compartment, S stands for susceptible, then the rate at which partnerships are changing, we can multiply that by the probability of transmission per partnership. And in fact, that's how we model the rate of new infections then. So mathematically, we can say that this force of infection, or again, the incidence rate, the rate of new infections per susceptible, is the product of this partnership change rate, Q, the transmission probability per partnership, B, and the infection prevalence. So that would be what proportion of your partners are potentially infected on average. And then I add the sum here because there may be different stratifications of the population that are being aggregated over when we do this, but I've omitted the indices for clarity here just because there could be many different stratifications that we consider. So how do we calculate this probability of transmission per partnership? I kind of already gave away the equation a little bit, or I tried to describe it. So if there's a true transmission within this partnership, as shown with the line here, the true transmission may occur after a certain number of sex acts, but then we have all these sex acts which occur later that are, as we call them, inert, so they're not able to lead to transmission. And so we need to account for these inert sex acts. What we model is the total probability of transmission per partnership, B, as 1 minus the probability of escaping infection after a certain number of sex acts. So if you remember those probability equations from, like, I don't know, high school math or something, the probability of escaping infection kind of decays towards 1 because we're constantly multiplying, like, let's say this probability of escaping infection from a single sex act is 0.99, then we put that to an exponent of how many repetitions of that we saw, and that would give us the probability of escaping infection, and then we do 1 minus. So maybe it's just easier if we look at the graph of these things. So we have an increasing number of sex acts towards the right-hand side. The Y is plotting this cumulative probability of transmission per partnership. And we can see that this equation approaches 1, but will mathematically, if possible, never to exceed 1. And I suggest, as I alluded to earlier, if we were to ignore this issue of inert sex acts, this product of just the numbers of sex acts times the probability of transmission per sex act kind of extends beyond 1, and it goes off to infinity. So it's really this gap between this angled dotted line here and the red line, which describes what proportion of sex acts are inert, or the reduction in risk associated with those inert sex acts. So what are some issues with this approach to modeling sexual partnerships? Well, the first of all is the issue that that transmission within these partnerships is effectively modeled as instantaneous. So if the transmission truly occurred at some specific moment in time, mathematically, we're taking the total cumulative risk associated with this entire partnership, we're calculating it as, like, effectively 1 instant in time, and then we're distributing that using this rate Q over the entire duration of that partnership. So in fact, partnerships are more risky, or there's more opportunity for transmission earlier in the partnership, and later, after transmission has occurred, there is relatively less risk, but we're basically applying that risk as a uniform function over that entire duration of the partnership. And so if some of these partnerships are, for example, 20 years long, there may be many things which change over the course of that partnership. The level of infectiousness as someone moves through different stages of infection is one example. The levels of condom use, which may change on a per partnership or even at a population level, depending on many factors. And including treatment. So once the infected individual starts ART therapy, which is to reduce levels of viral load within the blood, then their risk of on-road transmission is effectively 0. And so, that is not anticipated by this approach if we're projecting the model, projecting this cumulative risk 20 years into the future at a time point when those therapies weren't yet available. So this dynamic risk within the partnerships is not anticipated. But another issue that's kind of related is that onward transmission risk is effectively instantaneous even for the same specific partnership. So what I mean by that is that within the model, once someone becomes infected, they're immediately part of that prevalent infection term, the I over N, the number of infected people over the total population size. And so they're immediately at risk of retransmitting to any one of their partners. But in fact, what really occurs if the partnership is quite long is that transmission occurs, and then neither partner within that partnership can transmit to each other anymore. So there needs to be some kind of reduction in the immediate risk of on-road transmission, which is modeled, which is not included in this approach. The second issue is that we're forced to make a trade-off when we're adjusting for these inert sex acts. And by that, I mean, just to give a kind of clearer definition, after transmission within the same partnership. So they're no longer able to result in transmission. So most, not most, but the adjustment itself in some models has considered, oops, I am not plugged in on my laptop here, sorry, 1 second. The adjustment for these inert sex acts could consider the entire duration of the partnership. And in that case, we essentially have a risk that is applied due to this equation. So the slope of this line effectively represents the relative incidence or the relative rate of new infections is proportional. It's not exactly equal, but the higher this slope, the more risk there is associated with that partnership. So if the partnership is sufficiently long, then this slope you can see kind of decays and becomes more and more close to 0. It becomes flatter. So what we're doing is we're effectively saying, we know there's going to be a lot of inert sex acts later in this partnership, and we're just going to apply the average rate of risk, or the average risk associated with these sex acts over the entire duration of this partnership. So in reality, those inert sex acts occur later in the partnership, and we're taking them and kind of front loading them. So we call that basically front loading these inert sex acts. Really later in the partnership is where the inert sex acts occur, but we've added them, evenly distributed them throughout the partnership, and therefore we've essentially front loaded them relative to the true experience. Recognizing that issue, some modelers have sought to only consider one partnership year at a time. And so they don't actually consider the full duration of the partnership because there's so many inert sex acts associated with that, and they'll only consider up to 1 year at a time. But the problem with that is that there really are inert sex acts which occur later in these partnerships, and by this approach, they're totally ignored. So we're almost doing no adjustment by considering only 1 year at a time. So we're essentially ignoring these inert sex acts. A third approach is to actually consider all potential partnerships, because some people may have more partners than one within a given year, is to consider all of those partnerships as competing to infect the same individual. And we're actually going to consider the inert sex acts associated with having been infected by one partner, and then all other partners can no longer infect that same individual. So all of those partnerships are effectively considered within the same year. And this also completely ignores inert sex acts. It's actually redundant. We don't need to treat these partnerships as competing to infect the same individual, because that individual within the model will get infected at some given time point. And once they become infected, they move from that susceptible state to the infected state, and they're no longer at risk. And so this treating all partnerships as competing to infect the same individual is redundant with a dynamic that's already captured by the model itself. So to define the equations for these different approaches, we have this rate that I had previously described, the force of infection, where we have a rate of partnerships times the probability of transmission per partnership. And in this case, the A that's considered in our probability of transmission per partnerships is the actual total number of sex acts per partnership, which is usually defined by the multiplication of the frequency of sex with the partnership times the duration of that partnership itself. So it's all sex acts over the entire partnership. And then Q reflects the partnership change rate. That's in our kind of most classic implementation. If we're only considering one partnership year at a time, then A only reflects the numbers of sex acts per year, or effectively the frequency of sex in a given year. And then Q is how many partners people have in a given year. So it's not necessarily the change rate overall, which may be quite low if it's like a main and spousal partnership, but it's actually the total number of partners that they have in a given year. And that would effectively be at minimum 1. The final approach in purple, where we're considering all partnerships per year, then A still reflects all the sex acts per year, and Q still reflects the total numbers of partners per year. But in this case, we aggregate the total risk associated with multiple partnerships in a different way. And in fact, it's in a way that is similar to the way that we captured probability of escaping infection within a single partnership. So now we're effectively modeling what is the probability of escaping infection from not only a single partnership, but all partnerships over the past year. So Q is reflecting all partnerships that someone had over the past year. And you could actually simplify, you could combine the definition of B up here and the definition here. You could simplify this equation slightly. So you're essentially escaping infection across all sex acts from all partners in that year. But the critical thing with respect to interpretation of data is the definition of the numbers of sex acts that are considered being for all sex acts within that partnership or all sex acts within the year. Okay. Oops, and these are some definitions of those terms. Okay, wouldn't it be nice if there were a different approach to solve the same problem? So let's return to that problem statement. These compartments are homogeneous and they're memoryless, and therefore we cannot track these inert sex acts. That is, we can't distinguish between sex acts that occurred before or after transmission. However, what if we could track individuals who recently acquired infection, because we know those individuals will still be with the person who transmitted infection to them, at least until that partnership ends. And critically, we will also need to keep track of individuals who recently transmitted infection to their current partner. If that partnership persists, then they are also at reduced risk of on-road transmission because they've already transmitted to a particular partner. So we'll move those individuals after they either transmit infection or acquire infection into a new holding state, which is denoted in yellow here. So the further details are that within this holding state, Y, those individuals effectively have one fewer partners for the purpose of calculating incidence. And I note that mixing is unchanged because we do some math to model who has sex with whom and who partners with who within these models. And that isn't actually being changed by this, but for the purpose of calculating risk of on-road transmission, they effectively have one fewer partners. Now, how can someone leave this state, Y, this holding state? Well, it's effectively when they change partners. And that is related on average to the rate of, or the durations of those partnerships. So if you'll recall from a few slides earlier, the duration of the partnership was noted as a delta, and the inverse of that duration is one approximation of the rate of new partnership change. So, or the rate of changing partners. So for example, if the partnership was on average 20 years long, then someone might be expected to form a new partner every 20 years. Let's discuss in more detail how a more complex model might be adapted to incorporate this change. So earlier in the slides, we just saw an S compartment and an I reflecting susceptible and infected, but for the purpose of HIV, we often model many different infection stages because there's differences in the degree of infectiousness and other factors like including getting on treatment, in which case the infectiousness would reduce. And so these are different infection stages, but this stratification could reflect many different processes that we want to capture after someone becomes infected. So the first thing that we need to do is we actually need to add a new compartment Y for each different type of partnership. So we have P denoted, and in this case, in our model, we have 4 different types of partnerships. That's why there's 4 different stages or 4 different compartments that are these holding states, because once someone becomes infected by a particular partnership type, it's only that partnership type whose effective numbers of partners we need to reduce. If someone had 1 casual and 1 main partner, they got infected by the main partnership, then they have no main partners for the purpose of on-road transmission, but they still do have that casual partner. And so we need a different holding state for each different type of partner so that we reduce those by 1. So this new dimension is stratified by these partnership types. And we have the incidence per susceptible, which is the same as we had before. But new to this model, we need to calculate a per person rate of onward transmission. Normally, we only need to calculate a per person rate of acquisition. And so this is a new term, but they derive from the same kind of matrix-based approach to simulating overall rate of new infections. And those details are in the appendix. And then the final thing is that, and I should say that incidence of this onward transmission per infected individual, that is the rate at which those individuals could move into one of these holding states. The other detail is that the rate of incidence for both the susceptible and infected, that needs to be stratified by which type of partnership is being considered. So normally we aggregate the risk across all of these different types of partnerships when we define the total rate of incidence. But in this case, we're actually going to not perform that a summing operation and keep each of those dimensions of incidence as a separate term, a separate rate of incidence per partnership type. And then the final thing, as I mentioned, was we need to have individuals forming new partnerships. And upon doing so, they will leave this holding state and re-enter into a more classic state, as shown in red here, where they have 100% of their partners are potentially at risk of onward transmission. Whereas in yellow, we know they have at least 1 fewer partners for the sake of onward transmission. And so that rate is defined by the rate of partnership change. Okay, So what this allows us to do is that we don't need to adjust using the probability of escaping infection for inert sex acts. We actually have mathematically already captured it in this yellow holding state compartment. And the other thing is that we're no longer needing to anticipate changes to what that person's trajectory through infection stages or care might be, because we're not projecting into the future. We just look at their instantaneous risk. And so they may move between infection stages while in this holding state, and whatever changes associated with that for the purpose of transmission are inherently captured by this approach. So now we can actually just use the frequency of sex with any given partner as an instantaneous risk of their current transmission risk and their current numbers of partners rather than a partnership change rate. Okay, so now we're actually going to take those old instantaneous partnerships approaches, the three of them, and our new proposed approach, the effective partnership adjustment, and we're going to compare them in a compartmental model. So overview, we have our 4 different types of force of infection approaches compared. The instantaneous approaches, adjusting for either the full partnership duration, where inert sex acts for the full duration are considered. We're only going to consider, or we're going to also consider the instantaneous approach where only up to a year at a time is considered. And we're also going to consider that approach when all partnerships that someone has are treated as competing risks for that individual to infect them within a given year. And then finally, reflecting our kind of gold standard, even though we haven't validated this against more rigorous kind of alternative approaches, but our benchmark, I should say, in this comparison is going to be our new proposed approach, the effective partnerships adjustment. So considering these 4 approaches, we are going to compare 2 different mini experiments. One of them is we're going to keep the model parameters across all of the approaches equal. And then we're going to simulate the epidemic and compare dynamics of that epidemic simulated with equal parameters. So that's going to allow us to see what is the influence of these different, essentially mathematical equations on the overall simulated epidemic. But it's much more common for these models, as I alluded to earlier, to be calibrated to some data. And so we've done that as well. So we're going to recalibrate all the parameters, but then we're going to try to compare the attributable fractions of different types of partnerships. So that is to say, in a given year or over a given time horizon, which could be multiple years, we're going to say what proportion of infections could be averted if there was 0 transmission within a given partnership type. And that's after recalibrated parameters. So experiment 2 really reflects the types of resource allocation questions that would be a plausible application of this type of model. So we've built a model, we've assumed one of these approaches, and then we've calibrated to some data, and we say, okay, which of these partnerships could we prioritize for resources in order to avert the most types of the most infections? That's really what question 2 or experiment 2 is getting at. So coming back to equal parameters, this is experiment 1. To orient you with this graph before there's any data in it, we have the same colors as usual and these 4 different types of partnerships. And then what's being plotted is HIV incidence per person year among susceptibles. And we're plotting that across these 2 rows for lower risk population. That's everyone who is not involved in sex work, and also for female sex workers. And we're plotting it over time. And what we're going to do is plot the EPA, the effective partnerships adjustment, in all of these quadrants or facets for comparison with each of these other approaches. So now just considering the full partnership duration adjustment for inert sex acts, we can see that the comparison of that approach with the effective partnerships adjustment, they look almost identical. And there really is 2 different elements to this partnership duration, why it's similar to the effective partnership adjustment. On one hand, there is a front loading of those inert sex acts. So that's essentially anticipating inert sex acts in the future and adding them up front. And so that's actually going to reduce the modeled rate of incidence under that green partnership duration approach. On the other hand, individuals who become infected within that model are immediately at risk of on-transmission. That's the 2 halves of that issue with the with that approach. And so those two dynamics kind of balance each other out, and we happen to get quite close to our benchmark here, the EPA. The same can be said for both the lower risk and now here also for the female sex workers. As one of my profs once said, it passes the thick felt pen tip. So basically, if you had a thick enough marker, these two would be indistinguishable from each other. There are some minor differences, but they're quite similar. Now turning to the partnership year, where again, we were ignoring a large proportion of the inert sex acts with this approach. So in that case, by ignoring those inert sex acts, we're allowing much more transmission to occur under that partnership year approach, because we're totally ignoring the fact that these infections, once transmission has occurred, there's no longer any more risk within that particular partnership. And so we massively overestimate incidence using that approach, again, with equal parameters. So it is possible to recalibrate these parameters and we get something that looks more similar. But for the same parameters, that's kind of the innate effect of changing which type of approach we're using here. The influence for female sex workers is much less, but it is still a slight overestimation. And that's mainly because most of the incidents among the lower risk population, that is those who are not involved in sex work, derive from, in part, these casual partnerships, but also a large part to main and spousal partnerships. And it's really those main and spousal partnerships, because of their long length, that we really need to account for those inert sex acts. For female sex workers, there's relatively less proportion of longer partnerships, and so there's less influence of failing to account for those inert sex acts. Finally, we're looking at all partnerships per year, and in this case, we see a similar dynamic as the partnership year adjustment in blue here for the lower risk, but we actually see something quite different for female sex workers. And the reason that this occurs is because mathematically, it is impossible for the purple approach to predict a probability of transmission greater than 1. It is mathematically impossible. And in Eswatini, the relative rate of incidence for female sex workers is so high because prevalence is so high that we actually approach 1. We don't actually surpass it, I don't think, in this case. But by forcing all of the different sexual partnerships that a female sex worker may have to be competing within a specific year to infect that same sex worker, it's a redundant adjustment, and it pushes down the overall rate of incidence experienced by the FSW population in the model for that, under that approach. And so that's why, again, with equal parameters, we see a large reduction in incidence for FSW here. So now we're moving on to experiment 2, and we're talking about the attributable fraction, which is what proportion of infections could be prevented if we could have no transmission associated with a particular partnership type. So in this case, we're going to have 3 different types of partnerships: main and spousal, casual, and we're going to just combine the 2 different types of sex work partnerships here as sex work overall. We'll have the same colors, and we're looking at, starting from the year 2010, what if there was no transmission from a particular partnership type? What fraction of overall transmission would we reduce by turning that transmission off? This is called the transmission population attributable fraction, the TPAF here. The longer label didn't fit, sorry. And then we're first of all going to be considering a 1-year time horizon, but we're also going to project forward into 3 and 10-year time horizons as well. So looking at the effective partnerships adjustment, we have about 20% of infections transmitted by main and spousal partnerships, about 60% transmitted by casual partnerships, and about 25% for sex work overall. Comparing that to our partnership duration approach, we can see we have a slight reduction in the TPAF for main and spousal partnerships, a slight increase for the TPAF of casual partnerships, and quite similar for sex work overall. So overall, similar to our previous results in experiment 1, there's relatively little difference between our considering the full partnership duration and accounting for inert sex acts versus our proposed approach, the effective partnerships adjustment. The biggest differences come when we consider these partnership year or all partnership year approaches. For main and spousal, we see an increase in the TPAF from roughly double for main and spousal, from 20% to 40%. We see a large reduction in the proportion for casual partnerships down to 40%, and a small reduction for sex work overall. And this pattern is effectively repeated again for all partnerships per year across these three different cases. So the real difference comes in whether or not we're considering a full partnership duration or only up to 1 year at a time with this the adjustment for inert sex acts. Unfortunately, the partnership year approach, I would say, based on a systematic review I did of model structures, this is the most common that's used in the literature, and all partnerships per year is also often used. Relatively few models have used the full partnership duration approach. So I would say this is a pretty substantial implications for the insights that those models are able to generate, namely which types of partnerships with respect to their length should be prioritized for interventions to avoid transmission. These patterns also persist for different time horizons. So I avoided spending too much time on them, but the patterns really are the same across these different time horizons here. So to summarize these implications, when we're considering these partnership year or all partnerships per year adjustments, we're really ignoring a large proportion of inert sex acts that mainly affects longer partnerships. So we're basically going to be overestimating transmission in longer partnerships. If we consider the full partnership duration adjustment, then we front load some of the inert sex acts, and we slightly underestimate transmission in those longer partnerships, but the difference is really not that dramatic. And then with our effective partnerships adjustment, our proposed model, we explicitly track those inert sex acts because of that holding state, and we may get a just right attribution of transmission, although I would strongly say that we need to further validate our approach by comparing to an even better gold standard, which would be an individual-based model to really ensure that our effective partnerships adjustment is capturing these inert sex acts appropriately. And so coming back to our very original research question, what unmet needs drive transmission in Eswatini? And the answer, we can say, depends on the force of infection approach, which is not necessarily what we want, but it's definitely something that has implications for the existing body of research. And with that, I will thank many people and institutions who have helped contribute to this work. And I think we have about 15 minutes for questions. Thank you.
All right, if you have a question, feel free to type it into the box or raise your